I guess we can like start, and then people probably will chime in like.
Sounds good.
Yep, sure.
Okay. Let's get started. So hopefully you can see my screen again. We're going to go into some example projects. I realize I've already gone through a bunch of examples, but I want to dive in more detail and also give a sense of stuff being done in my own lab at McGill and Mila. So these are the themes that I highlighted before: improving operational efficiency, gathering information, forecasting, speeding up simulations, accelerating scientific discovery. So let's dive into some examples from within these themes. Improving operational efficiency. So the example that I want to touch on here is motivated by electrical grid optimization. So balancing the electrical grid requires solving a non-convex optimization problem, AC optimal power flow. So what balancing the electrical grid really means is making sure there's enough power available to meet demand at any given point. And the amount of power, as I've mentioned before, varies depending upon what is available. If you have fossil fuel generation, you can control that. But if you have solar and wind, you cannot necessarily control that. And so you need to work out what power needs to come from what sources to make sure that the lights aren't going to go out. But to do that, you need to solve a non-convex optimization problem. Non-convex optimization problems are famously hard to solve. There aren't good computer science algorithms for doing that. This is specifically what the problem looks like. It is a quadratic problem, but it is non-convex. So typically, what people do in practice is, since there aren't good ways to solve non-convex optimization problems, the power grid operators, the people running power grids, typically linearize the problem. As you can imagine, taking a quadratic problem and linearizing it is not good. You end up coming up with a very suboptimal solution, and this, in practice, wastes large amounts of power, especially with solar and wind power. But this is what is done. You might ask, why don't you just use deep learning to magically solve it? Because that's what we can always do, right? No. Typical deep learning algorithms cannot do this. And this goes back to this whole constraint satisfaction thing, making sure that you have the engineering constraints built into the algorithm. The typical way for a deep learning algorithm to solve something like this would be to say, let's minimize the objective function and also minimize violation of the constraints. So you have a penalty for not minimizing the objective function. You have a penalty for violating the constraints. You trade off between the two. However, that fails completely because you are likely to slightly violate the constraints and minimize the objective function. Slightly violating the constraints is not good. It's like having your train slightly go off the rails. The whole system crashes. Because this is physics equations, right? Like, if the power doesn't flow on the electrical grid, then everything breaks. So you really need to make sure you satisfy the constraint. And so we have a constrained deep learning approach that can satisfy can solve non-convex optimization problems approximately. And this is work jointly led with Priya Dunthi. So the goal here, the problem that we're solving, is to get an approximate mapping from X to Y, where X is a set of parameters parameterizing a family of optimization problems. So in this case, X is like these various different constants here, which is like how much power is available, how much power is needed, the particular way in which the power grid is set up. It parameterizes all of those things. And you're trying to minimize some objective function subject to some inequalities and some equality constraints. You give an X, you output the optimal value Y. Now, what we're going to do is we're going to have a deep learning approach for solving this, but it's going to be somewhat unconventional in a few ways. First of all, you are not going to output all of the variables. You're going to output only some of the variables. Then you're going to solve for the remaining one. That's called completion. Then you're going to correct for any deviations from inequality constraints by using gradient descent, and then you're going to train the entire thing end to end. Let's go through each piece and why it's there. First of all, there's going to be a lot of messy equations here, but the idea is really simple. Suppose that you have an equality constraint in your optimization problem. That means you've lost a degree of freedom. Like, if you have one equation you need to satisfy, you have one fewer degree of freedom in your solution space. So you should predict only as many variables as you have degrees of freedom. If you have k equality constraints, you should predict k fewer variables. And then you can solve for those using the equality constraints. That's what we do. The way you solve for the other variables is numerically, things like Newton's method. And those methods are effective, but they are not differentiable. And if you're going to try to train a neural network, you know that you need something that's differentiable. So what we do is we use the implicit function theorem to get some implicit derivatives of these variables, the new variables that we're solving for with respect to the variables that we've predicted by the neural network. That allows us to calculate the derivatives we need to do a backpropagation through the whole thing. So that's why we're doing the completion. And then the correction process is, suppose that we've satisfied the equality constraints by design now, because we chose our new variables in order to satisfy the equality constraints. For the inequality constraints, we assume that we have all these variables already. Now let's push them towards satisfying the inequality constraints. So the green manifold here is everything that satisfies the equality constraints. The blue subset of it is the place where the inequality constraints are also satisfied. We're going to take some steps of gradient descent until we're in that region, the legal region. And the gradient descent is gradient descent on the outputs. It's not gradient descent of the neural network parameters, which is the standard one. It's gradient descent of the outputs of the network. And in a few steps, we fall within this region. Now, in practice, it only takes a few steps. It wouldn't have worked for satisfying the equality constraints because we would have oscillated back and forth instead of ever actually satisfying the equality constraints. For the inequality constraints, you can do this. And we train the entire thing end to end to minimize the objective function, also to minimize any deviation from the constraints. And in practice, this works perfectly. You don't get a violation of either the equality constraints because of the completion procedure or the inequality constraints because of the correction procedure. Here is the performance on optimal power flow, though it can solve a lot of other things as well. It's a general framework. You can compare it against, so blue is our method, top line is the traditional methods. This is if you train a neural network using the soft loss approach I mentioned before, where you're trading off against violating the constraints and satisfying and optimizing the objective function. This violates all the constraints, so nobody would ever use it. This is a supervised approach where you've seen a bunch of good solutions and you're trying to copy them, but this also fails to satisfy the constraints. It can't generalize. And this is if you add in our correction procedure to those approaches, and it still doesn't work. Here are various ablations of our method showing that all the different approaches are actually, all the different ingredients are actually necessary. But the important thing is comparison against the optimizer. You can see that we are attaining basically the same objective value. There's a slight optimality gap. It's slightly less efficient than the traditional optimizer, but it is, in this case, 10 times faster. And if you allow parallelization on the GPU, which is something that deep learning can do really easily, but the classic optimizer can't do, then you could probably get it orders of magnitude faster even than that. So what we've done is we've created an algorithm that is at a practically fast speed, so that it can actually be scaled up. And it is solving a non-convex optimization problem while preserving constraint satisfaction. So making sure you're not going to get a blackout on your power. We'd like this to be used in other applications as well. There are many settings where you need to solve non-convex optimization problems, but have like hard constraints that your engineered system needs to satisfy. Okay, here is another application. If you got lost in all the equations, now is a good time to tune back in. There are going to be fewer equations. Remote sensing for agriculture. Mapping crops and forecasting crop yield are really essential to averting food insecurity because climate change is threatening food supplies globally. we need to have better understanding of how crops and crop yield are changing. But agricultural data is sparse and it's imbalanced across different crops and locations. People have been trying to use machine learning with satellite imagery to assess where crops are. For example, many governments need to know where farmers are planting crops, what kinds, and what the yields are in order to plan ahead for subsidies, to plan for food aid to certain regions, and to implement policies regarding agriculture. So this is really critical information, but the data don't exist, and the data don't exist well enough to train machine learning algorithms to produce more data. You can see from this data set, which we have from our partners at NASA Harvest in the US, that the really good data, which is the orange data, is only available in a select set of locations around the world. That's the data where we know what kind of crop is there. The blue data is available in more places, but that's just saying, is there a crop there or not? So is that farming or not farming? Not very helpful. So we develop algorithms that can use very, very little data and generalize from locations where there's more data to locations where there is less data. This is work led by student Gabby Tseng in collaboration with Professor Hannah Kerner. And the goal here is to be able to take a situation like you've seen, if you're the algorithm, you've seen coffee in Kenya and maize in Brazil, but you haven't seen coffee in Brazil or maize in Kenya. How do you learn that really fast with very minimal data? So some background on meta learning. Meta learning refers to learning in such a way that the model can adapt quickly to a new task with new data. And in particular, often people use a popular framework called MAML, which is model agnostic meta learning, where a neural network is trained specifically to maximize the effectiveness of gradient updates on new tasks. What that means is, if this is your learning process, if this is parameter space, you're moving to, normally you would be moving to minimize the loss. Here you're trying to move to minimize the loss if you did a parameter update. So you're moving in a direction, you're moving to a point here in parameter space where if you did a gradient update with data from task 1, you'd end up in a good place for task 1. If you did a gradient update with data from task 2, you'd end up in a good place for task 2. And if you did a gradient update with data from task 3, you'd end up in a good place for task 3. The goal is to end up with a network that's really adaptable, that's able to quickly learn a new task. And you're actively optimizing for this in your gradient descent process. Now, this is how MAML works. It's a training paradigm that can run across neural network architectures and tasks. We're going to add on to MAML, and we're going to build specifically 2 components onto MAML. The first one is we are going to incorporate different metadata about the task being learned. Somehow, the meta learning community has not really incorporated the kinds of domain information which are really common in remote sensing, where something is being observed and what kind of thing you're observing. In the context of agriculture, that's geographic location, lat long, and crop type. And we're going to incorporate this information into the representations being learned by the MAML model. You're going to take that information, you're going to encode it with one neural network. You're going to take these 2 outputs in the neural network, and you're going to just do a linear transformation with those encodings in order to modulate your hidden representations in the MAML model. So the meta learner is now able to incorporate where in the world the data was coming from and what kind of data it was, like what crop. The other component is forgetfulness, so tasks that the model memorizes. Once you remember, the data is really imbalanced. So suppose that you see a lot of data from one particular setting, the model might learn that really well. By the time it learns it really well, that data is probably not helpful anymore, and you don't want to just overfit to that task and forget about all the others. So you drop data dynamically from training once the model starts performing really well. These two components are designed to enable you to generalize across many different settings. So we can see, I'm going to show this in the crop harvest data set, across different locations, how well the different algorithms perform, and our task-informed meta learning approach blows all the other approaches out of the water. We also compare it against various other approaches that aren't shown here that are a little bit fancier too, which it also beats. In particular, I want to highlight the Brazil task, which is notable for having very little data. And here, our approaches are just far, far better than everything else. And the reason is because they have the ability to generalize, to know where data is coming from and what kind of thing that data is coming from. Maybe they haven't seen data in Brazil, but they've seen nearby data, which is going to look similar. Maybe they haven't seen data on this crop, but they've seen data on similar crops. And you can see as training set increases, the other models start performing better, but the performances are really low when there's very little training data, which is very common in practice. And so something like task-informed meta learning can actually perform well zero shot with no new data. This is the kind of thing that we really want to improve equity in remote sensing, because having really imbalanced data sets, really geographically or task imbalanced data sets is going to be more and more valuable as we consider greater diversity of use cases. This also works on regression. That was a classification task. This is a regression task. It also works really well. And we've actually seen that it works in other contexts too. Like we are using this in optimizing building energy use as well, where generalization is across different buildings. We've also seen that this can be useful in monitoring carbon flux, where various parts of the world have less data collection. Like there is, there is less data collection in the global south for carbon flux, in particular in Africa. And so inferring data from under monitored locations can make the data collected there be much better. So you don't have the situation where African stakeholders just have to deal with really shitty data. Okay, so next, the next example that I want to touch on is specifically on the gathering information theme. And this is again with remote sensing. So the set of problems that this can be applicable to, again, agriculture, but also forest management, many other climate relevant applications of ML. We've seen many applications involving satellite imagery. And the challenge that we want to address here is really, what does it mean to work with satellite imagery? And I think a lot of machine learning people looked at these kinds of images and said, oh, well, this is an image. That means I should use computer vision. And it's a really natural thing to do, because you have a tool. Everything looks like a nail if you've got a hammer for nails. But it turns out that satellite images are very different from natural images that computer vision algorithms are typically developed for, like ImageNet. And because of that, the differences we'll get to in a moment, the methods that people have used are often not very generalizable. They don't generalize across geographies. They don't generalize across different tasks. They're computationally very intensive. Like very big models for ImageNet, which aren't really what you want if you are a government trying to implement some deforestation monitoring or agriculture monitoring algorithm. And they're very sensor specific. So if you are used to ImageNet, maybe you're used to RGB images, but satellites can use hyperspectral imagery as well, and other kinds of data as well, like elevation maps that can be climate features thrown in that can help you. So you're losing information, and you're not necessarily matching your algorithms to the tasks. And so we just put out a paper that is focused on really understanding what the nature of satellite data is and how to build algorithms that's sensitive to it. So the core insight is we're going to leverage the structure of remote sensing algorithms. And in particular, we're going to leverage the multimodal data structure, so multiple different sensors, and multiple different data sources. And we're also going to introduce the fact that this is temporal. And so you have not just a single satellite image, you have many images over time and watching the land as it changes. So what we're going to do is we're going to throw in as much data as we have over the whole world: satellite images, elevation maps, precipitation maps, other things. And we're going to stack all of that, and we're going to get this big stack of images with lots of different features. And we're going to do that over time. And then we are going to train in a self-supervised way. So we're not going to have any downstream tasks. We're just going to we're going to use a masked autoencoder. So we're going to throw out pieces of this input, and we're going to try to reconstruct it from what's there. You could throw out random parts of your data. You could throw out particular time points. So like you throw out March, but you have April and May. Can you reconstruct March? Or you throw out the green channel. Can you reconstruct it from the red and the blue, etc.? And crucially, we're actually going to completely ignore the image-based structure. We're going to do this on a single pixel level. This sounds like the worst thing if you're thinking about computer vision. You're not looking at the image. You're looking at only one pixel. How could you possibly have any value in this? Well, it turns out that actually, if you have all of these features like red, green, blue, hyperspectral, precipitation, elevation, blah, 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 you actually have a lot of information at that pixel. And the pixel structure over time is more valuable than the spatial structure. And so what we're going to do in this context is we're going to learn a representation of the data that is then useful in any downstream task. And so once we've learned this representation using the masked autoencoder, that's a purely self-supervised thing. That's done beforehand. And then when you actually have a task, you just use these representations. You do regression or random forest on the encoding of each input pixel. And then that is something that you learn, but it's a very fast refinement process. You basically already got a useful representation of the satellite image, or as each satellite image pixel, and then you can learn whatever downstream task you want. If you have an image with multiple pixels, you average the predictions for individual pixels over the entire input image. You know, like a mixture of experts thing. We are going to evaluate this across lots of different tasks, many different input channels, many different time steps, lots of different training set sizes, from very small to very big data sets, many different task types across lots of geographies. And we find across all these different diverse tasks that this is able to outperform larger models, even on data modalities it wasn't trained on. So here, there is a data set on identifying trees, for example. And the typical way in which this is done is looking at an image of lots of trees, an image of a forest. And what we're doing is instead, we take each pixel of that image, we encode it using our learned encoding, and then we fit a very simple classifier to classify what kind of tree it is based on just that one pixel. And then we have a mixture of experts over all the pixels in the image. And we actually outperform the image-based methods. And that's because we're really leveraging the structure of the data by understanding how satellite imagery works. Lots of different features and over time. You can see here we outperform various models on TreeSat, even models that are much more computationally intensive. On Eurosat, which is another satellite imagery task, we're 1,000 times smaller than the state of the art, but we still outperform state of the art. So this is monumentally more computationally tractable and also better. And it is, again, an unsupervised or a self-supervised approach with just a slight amount of fitting to your data at the end. So we see this kind of approach as really the future of remote sensing, where it's both more equitable because it's lower costs in training something, and also just better because it's really fit to the kind of data that you're working with. And this is a theme that you see over and over again in these kinds of applications. Really thinking about what the data and the task are and how you can make your algorithm shape your algorithm to that task. I talked a bit earlier about speeding up simulations. So how to use machine learning to make parts of physics-based models faster. Another approach, instead of approximating the physics-based model, is you can actually do super resolution. The context for this particular set of applications is that you have very slow climate models that are producing very coarse resolution predictions. So this is a typical set of data for the world. You can see the grid cells. They're like hundreds of kilometers big. If you were trying to decide how weather or climate is going to change for your particular city, that's not going to be very useful to you. How do you increase the resolution of this picture? Well, you can do super resolution, take a blurry or coarse resolution image and make it a high resolution. This is not, you can't do it arbitrarily well, but you can do it, you can make this significantly better. And so there are a couple of papers I want to talk about that we just put out. And the first paper has to do with doing super resolution with conservation laws. So in the domain, this is called downscaling. It's really confusing. If you work in this space, you're going to have all these different kinds of situations where one word means one thing in the machine learning context and another means something in the applications context. So in this case, upsampling means downscaling. Very confusing. So this is like super resolution is the same as downscaling, is the same as upsampling. And what we're trying to do is we're trying to take a single pixel and we're trying to subdivide it into smaller pixels so we get a higher resolution image. But we would like to preserve the physics laws, conservation laws like conservation of mass, energy, and momentum. So if the pixel is subdivided, then the subpixel value should sum or average to the original value. Like, for example, if it's water mass, then the total amount of water in all the subpixels should be the total amount of water in the original pixel. This is useful to improve accuracy. It's also useful from the perspective of credibility. If you're trying to get people to actually use this, they clearly want to make sure that you're not grossly violating physical laws. Now, what we have come up with here is we add a hard constraint with softmax, where we normalize these outputs according to the original pixel value to ensure that they actually do sum up to this. And this is differentiable, so you can differentiate your whole procedure. It also ensures positivity, which is good for something like water mass, which cannot be negative. Second innovation that we have is going to use a cool new thing called the Fourier neural operator. Now, as background for this, a functional operator is just a map between functions. It takes a function and it outputs another function. So you can consider an image as a discretization of a function. The function is basically the infinite resolution version of the image. Like if you see individual pixel values, there's actually some physical object which is being instantiated by that image. And the pixel values are a little discrete, grainy version of the real function, the real image out there. Now, Fourier neural operator is a way to use a neural network to parameterize a functional operator by working with coefficients in the Fourier domain. Basically, that just means they can learn a map between functions, and they do it with Fourier coefficients instead of with normal coefficients. Fourier coefficients are useful if you're working with anything that's sort of like signal processing-y or differential equations-y. In particular, like fluids, climate and weather is basically just fluid flow in like the ocean or the atmosphere. And those are differential equations. And like do some keyword search, differential equations, fluids, fuzzy things like that. They work well with Fourier coefficients. That's how people think about them. Acoustics is also really good for Fourier coefficients. That's sort of the natural way to think about them. And so the Fourier neural operator is a technique that's been used to process this kind of data. And so we adapt this to downscaling, where the input is a low-res image, the output is a high-res image. And what we're going to be able to do is we're going to actually be able to create an infinite resolution version of an image. So sort of an arbitrarily good super resolution. We take our image, we throw it into a neural network, and then we create a function from the output of the neural network. That function is sort of the infinite resolution version of the image. Then we process that with a Fourier neural operator, and we get our final version. The goal here is that we're actually able to take a downscaling operation. We're going to make that be as good as we want. So suppose that we are going to try to take an image and we're going to try to increase the resolution by 2 times. Okay, so we can train our Fourier neural operator based downscaling approach to do that. And we can compare it against various other approaches. And so this is the upsampling factor 2 times is these dark blue points. And you can see that we are better than all the other approaches with respect to increasing the resolution by 2 times. But the really cool thing is that in our case, you train on 2 times resolution improvement. You can actually generalize 0 shot to 4 times resolution improvement, or 8 times, or 16 times, without seeing any of that data, because you've got this infinite resolution image, which is just a function which you can discretize at whatever resolution you want. And so you can treat this as a 4 times resolution improvement. And actually, our 0 shot generalization outperforms the state of the art on 4 times downscaling. So we can 0 shot generalize and beat state of the art, even state of the art algorithms that were trained to do exactly that. I don't know if that fully came through. I'm trying to cover a lot of things really fast. We also did this on Navier-Stokes. This was on predicting like water content in the air. This was Navier-Stokes. Same things with Navier-Stokes equations, which is like famously hard to solve. I can quickly touch on the last application for my group that I wanted to cover. This is using graph neural networks to evaluate different catalysts in materials science. So currently fossil fuels are required for many settings in heavy industry and transportation, and electrocatalysts can allow low carbon electricity to be used in place of fossil fuels or converted into electrofuels. For example, if you have electricity, you can use an electrocatalyst to store that electricity in hydrogen or something like that. But we don't have very good electrocatalysts, and so we're designing them using chemistry simulations like density functional theory. However, these kinds of chemistry simulations are very computationally expensive to run. So machine learning is increasingly being used to speed up the innovation process. Now, currently, machine learning methods in this area use graph neural networks, but these are still pretty time intensive. People build really big ML models, and you have to evaluate a lot of different things. You have to evaluate lots of candidate catalysts. And that means that it's not as useful when you're trying to really search over large space. So we do a few different things in some recent work in this area. In particular, we're trying to work with a property that is really important in this kind of area, which is invariance or equivariance. And the challenge is that if you have a molecule that you're trying to predict some property of, like how good a catalyst it is, if you rotate your molecule, it's the same molecule. So you need to work with a model that will output the same result for this and for this. Rotating something or translating it doesn't change what properties it has. So invariance means the output is preserved under a transformation, like predicting energy. Equivariance is something where if you transform the input, the output changes too. Like the forces, if you're trying to predict forces, you rotate the input, you rotate the forces, because forces are vector quantities and energy is a scalar quantity. So invariance and equivariance are related concepts. Sometimes you want one, sometimes you want the other. A common solution, and if you've seen anything in this area, which you might possibly have done, it's like disturbingly large amounts of math. You'll see things like Clebsch-Gordon tensor products Who knows what those are? I have a PhD in math. I have no idea what that is. There's just vast amounts of math, and it's arguably like mathematicians throwing in math for the sake of it because we want to feel useful. Now, this means you end up with really complicated neural networks that are extremely hard to understand and also more computationally expensive. So we're going to do a much more obvious thing to create invariance and equivariance, simpler, lighter weight. You get a faster, actually better performing model. We're going to outsource equivariance to the data. I'm going to skip over the representation theory. There is some math here, but you don't need the math. You basically just transform your data. It's like a data augmentation approach. You're rotating your data. You are averaging your outputs over the different transformations of your input. And you're going to create a model which is able to be robust to however you rotate your data. Again, skipping over the details, you end up in a situation where you have a model that, this is our star model, that is both extremely accurate, so it is the most accurate of any model on this open catalyst data set, which is evaluating catalysts for low carbon energy applications. And it's also almost as fast as the fastest model while being better than the best model. So again, the goal here is to have a lighter weight model by not having as mathematically complicated a model, outsourcing equivariance and invariance to the data through this like data augmentation approach. Again, I didn't really go into the details, but really thinking about what the problem needs and building a model that is tailored to that. Here's another data set where we also are as good as the state of the art while being much faster. Okay. We've seen examples of all these different areas of ML and climate action. I'll skip over this paper. I'm going to jump to the next section, which is responding to a question that was raised earlier. Isn't machine learning also making climate change worse? And yes, it absolutely is. And in lots of different ways, probably more than you think. So there are different ways to assess the climate-related impacts of machine learning. There are many different ways in which machine learning has a climate impact. The direct emissions associated with machine learning are when you run a machine learning algorithm that uses energy and is run on some servers, and that has some carbon cost. We'll go into that in a moment. The sort of indirect effects on climate change can be either you're using it for a climate positive application, helping climate change, or you're using it for an application that's bad for climate change. And then there are system level impacts. We're going to go through each of these in turn. So first of all, let's go through emissions from the computation and hardware. This is probably what people think of most when they think of negative effects of machine learning models. You may have seen some of these plots. Depending on the machine learning model that you are running, you could be using anywhere from basically no energy, like charging a phone, to the yearly energy of an entire home in the US. I think this was created by authors in the US. Most ML models are not that big. You can look here, see what kinds of models you're training. Maybe you're training fully connected networks. That's like charging a phone. Maybe you're training vision transformers. That's like driving a mile or using a gallon of gasoline. Some people are training like multi-billion parameter transformers. That can be extremely expensive. And certainly if you're training something like GPT, that's very expensive. So this is just to give a sense of the energy associated with training different kinds of models. Now, yeah, varies a lot. Sorry, I forgot I put those arrows. There is not just energy associated with, let me go a bit out of order here. There's not just training. There are several different phases to machine learning model development. There's development, there's where you're working out lots of different possible models. There's training and there's inference. And it's important to remember that each of these has a different frequency, but also has a different footprint. So development is very intensive, but is done very rarely. Training is done more frequently because you're updating your data and you needed to retrain your model. But then the most frequent thing is inference. And so each of these has sort of like, as you go from left to right, it's increasing energy per run, but it's also run less frequently. So it's important to remember those two factors. Because of these counterbalancing factors, each of these can contribute, maybe not comparably, but they all contribute meaningfully to the overall energy. Okay, so that's the operational emissions, the energy consumed during computation. And avenues to improve that are using efficient computational techniques, efficient algorithms, and the like sort of efficient computation in the data center itself, like cooling and waste heat use. And there's also using renewable energy to lower the carbon cost of producing that energy. Though to some extent, if you're using renewable energy, but forcing somebody else to use high carbon energy, that's not necessarily a savings if you've like just moved the accounting to somebody else. Like ultimately, it's always better just to use less energy because there is only so much energy that can be produced, especially from low carbon sources. There is the second component though. The hardware also has an energy cost, and this is also part of the sort of direct emissions associated with machine learning computation. The embodied emissions from production and end of life of hardware. There's mining and production, there's transportation of those materials, and there's disposal and recycling. These all have energy and emissions costs. Now, overall, what do all these things add up to? Actually, not that much, surprisingly little, and it's stayed pretty flat so far. This might change with a lot of large language models. But actually, all of the ICT sector, so all of sort of digital technology, is only between 1% and 4%. You ask different people, you get 1% to 4%. Here it says 1.4, but maybe it's up to 4%. But that's all of digital technology. AI is some relatively small fraction of that. It's unknown, and it potentially is increasing. It's relatively small, surprisingly, given how much we rely on digital technology. This is definitely something we should bear in mind if one's running really large models. If one isn't, it's probably not that big. These are the different factors to bear in. However, we're just getting started on negative impacts. We talked about ML applications that can make climate change better. There are also ML applications that can make climate change worse. So you can use these different kinds of machine learning strategies like data mining and remote sensing for all these positive things. You can also use them to accelerate emissions intensive activities, and that is being done a lot. So in the oil and gas sector, AI is being used to do various things, some of which might potentially lower emissions, but most of which probably are increasing emissions. AI has boosted production levels in some cases by as much as 5%. That is a huge increase in the amount of oil and gas being produced that is serving to run counter to climate goals. It's very clear that we can't immediately stop oil and gas consumption as a society, but we also should not be increasing production and exploring new oil and gas reserves. And AI is expected to generate $500 billion in revenue for the oil and gas sector just by 2025. This is a huge impact. It's very important to remember that what the algorithm is being used for can often have a very outsized impact compared to what the algorithm is. Even this is not all of the negative effects of machine learning on climate change. There are systemic impacts, which can actually be good as well as bad. We talked a little bit about rebound effects. Making things more efficient can reduce costs, which means that people may use a service more. Like, suppose you make driving more efficient, or make production of a product more efficient. That may mean it's cheaper and people will consume it more. That can partly counterbalance the savings you got through making it more efficient. There's also more subtle changes too, like changes in consumer behavior. The elephant in the room here is online advertising. Machine learning has enabled a huge increase in online advertising and increase in societal consumption patterns. Nobody's measuring how much that's actually impacting consumption of resources, but it's almost certainly enormous. Most tech companies rely on online advertising as their major source of revenue. So this is an enormous way in which AI is increasing consumption of resources and probably greenhouse gas emissions. There are also other things like communication and education. This can be both good and bad. Machine learning is being used both in educational positive initiatives regarding climate change, and really, I'm very worried from the perspective of large language models, how easy it is to generate misinformation in the climate and in other contexts. So there are these system level impacts. Nobody's really measuring them. If you think overall about all of these different things, you have the compute-related impacts, which are easy to measure, relatively small, immediate application impacts, both positive and negative, medium-sized, and then the systemic impacts, very, very hard to measure, but probably really big. We need more data on all of these things. And the goal of this figure is not to say you should not be considering compute-related impacts. You should not be considering the things that are hard to measure. But you should recognize that there are all of these different ways in which machine learning work can impact the climate. And specifically, what do you take away? If you're thinking about the computing-related impacts of machine learning, measure your carbon footprint. There are tools out there, like all these various tools, where you can assess how much emissions your ML model is generating. Just put them into your code, you can get an estimate. Reduce your impacts by choosing more efficient models, and also training fewer models, potentially. But if you're working with relatively lightweight models, that's not that much of a difference. If you're working with big LLMs or big vision models, maybe that's something you should consider. So monitor it and maybe reduce it. Application-related impacts. Quantify and evaluate the application impacts where possible. Try to think about what your algorithms are going to be used for. There are all kinds of implicit choices that we make. A good example here is self-driving technologies. Suppose that you are working on self-driving technologies. Those could be used for cars. If you go back to the societal behavior slide, if you make driving easier, people are going to drive more, and you're going to end up with more personal car use. It is expected that self-driving cars will actually make climate change worse because of this, even if each mile driven becomes a little bit more efficient, because people will want to drive more. However, if you're designing self-driving technology with buses in mind, that could make climate change better. So think about how the way in which you're designing algorithms is shaping the impacts from a climate perspective. Be transparent about the impacts in publications and with stakeholders, both quantitatively and qualitatively. Maybe you can't measure things exactly, but think about these issues when you're thinking about the full pipeline from research through deployment, and shape the impacts through your work, because oftentimes we as technologists don't think about ourselves as having agency for how people use our work. Our work gets used, And inevitably, that has consequences for society, and we are in the best position to actually make choices about how our work is being used. Consider the system-level impacts of your work. All machine learning applications may potentially have an effect on the climate. For example, self-driving cars, recommender systems. If you're working on recommender systems, that is going to have an impact on the climate. I'm not saying you shouldn't necessarily work on recommender systems. There are advantages to some things, and one doesn't have full scope of choosing what things one works on, whether in academia, industry, the public sector, elsewhere. One doesn't necessarily have choice, but where possible, consider how to shape the implications of your work. There are choices that we can make to some extent about what we work on, and bring climate considerations into how you build an application, as well as what applications. Maybe you can say, okay, maybe I'll work on self-driving buses instead of self-driving cars, for example. You can also initiate broader policies like internal carbon pricing, conditions on projects or project realized. Maybe you have the ability to do that. Not everybody has the agency or luxury of doing so. Also, don't forget about other social and other environmental impacts. Obviously, machine learning models have lots of other implications. The applications of one's work are broader than just carbon. Okay, so having talked about these different intersections of machine learning and climate change, in closing out, I want to turn to some important considerations for research and deployment. When working on machine learning for climate action, it's important to understand the broader pathway to impact in which the machine learning is situated. In particular, it's necessary to scope the problem, understand what other tools and approaches already exist, and understand how the machine learning, if it's needed at all, will interact with these existing tools and approaches. This relates to some earlier questions. So downstream from the machine learning, it's important to understand how the solution will be analyzed and deployed, and what potential other consequences or side effects it might have in terms of things like rebound effects, in terms of equity, impacts, and so on, and incorporate these considerations when developing the algorithms in the first place. We really want to think sort of backward from what's going to happen downstream. What this means in practice is that machine learning for climate it's not a field where the lion's share of problems will be solved by just picking up some benchmark and running with it, like getting a small improvement on ImageNet. Of course, benchmarks are a good way to get started, but they're not necessarily where the impact is. It's a field where the process of understanding the problems and the domain is really important, going through the process of gathering data, setting up the problem yourself. This can be a lot of work, but it's really rewarding. It can generate a lot of insights and opportunities to ask novel research questions, and also just really have impact in a way that machine learning often doesn't have. So a part of developing this domain understanding involves getting a sense of what data is out there. Data, simulators, evaluation metrics may already exist. They may need to be created. You may not have data sets. The data side, creating data can mean different kinds of things. It can mean data collection, also just annotation or collation. Maybe the data exists, but it's in some old Excel spreadsheet that some government organization put together years ago and doesn't work with is not easy to ingest into Python. We've had this. Maybe it's in 1,000 different Excel spreadsheets that you need to load together. This also happens. Maybe you need to deal with licensing the data. It's really messy sometimes, but it's really rewarding. It's worth noting that different communities also have different notions of data. So it's important to work together and calibrate expectations in this respect. I can't tell you how many times, for example, somebody says, oh, I have lots of data, and they mean I have 10 data points that they worked really hard to get. And I have to explain to them that that is not enough for most machine learning approaches. And so maybe they should be looking at some other kind of algorithm. Importantly, evaluation metrics are key. I'm jumping the gun a little bit here. So I first wanted to talk about simulators. This is really relevant in a lot of different contexts for control and optimization problems where you're in a power grid, buildings, heavy industry, these kinds of settings. Often you need simulators to generate lots and lots of very plausible real-world scenarios, because you can't necessarily experiment on your power grid. You need a reliable simulator. Evaluation metrics are important to understand how the method, what it means for the method to be successful, measure side effects, negative consequences, other things. Developing good metrics requires involvement from many different stakeholders often, also reevaluation to make sure the metrics continue to make sense over time, iteration with those stakeholders. A few resources I can point to here include, we have a dataset wish list at Climate Change AI. I'm going to talk more about Climate Change AI in a moment. It poses different kinds of data sets that can be useful to create. There are entities like the Lacuna Fund that can actually give you funding for creating data sets. We also offer funding at Climate Change AI for data sets, particularly in low and middle income contexts. And there is a publication venue specifically for creation of data sets at NeurIPS. When developing data metrics and benchmarks, the broader conversation on responsible AI is also very applicable. And this can play out in different ways. There are many ways where data and algorithms can create or perpetuate bias. For example, when working to pinpoint ways to make buildings more efficient, it's important to understand how factors like housing discrimination and generational wealth have affected the current state of which buildings are efficient. Data on buildings is also unevenly available across geographies, which can potentially bias interventions. We have data more from certain geographies and communities. Modeling choices can also perpetuate bias. For example, physics-based weather models are often calibrated based on observational data, and the choice of calibration data affects who the model performs well for. For example, reanalysis data in weather is often very bad in Africa. This is a known problem. And so if you've tailored your models using reanalysis data, it's just not going to perform as well in Africa. In addition to bias, trustworthiness and accountability are also important. We discussed some aspects of this earlier. And then equity considerations are really important, considering the intersection of responsible AI and climate justice. Important actions in this area include centering a wide variety of stakeholders. For example, not just working with, in the agricultural sector, not just working with like large scale industrial ag. I can't tell you how many startups there are that are using ML in the context of industrial scale agriculture, but not considering smallholder farmers, which is what most farmers are across the world. Ensuring that ML capacity, compute expertise, and access are not just concentrated within a few institutions and geographies, but making sure they're democratized so a broad set of stakeholders can participate in and benefit from ML for climate work. I'm really glad that there are more summer schools across a wider variety of geographies. Really, really happy that this is happening. Avoiding digital colonialism, like people from developed countries using data from developing countries with little involvement or benefit to the populations whose data are being used. For example, by exploiting differences in privacy regulations around personal energy usage, for example, or analyzing satellite imagery from afar without actively contributing something. There is a lot of this sort of folks from some famous institution in North America sort of airdropping in, being like, let's take your data and solve your problems, and not actually do anything. This can be a lot to keep in mind. So if I had to impart one meta-level tip here, it would be to work with the correct stakeholders. Make sure that these considerations come to the fore. This includes researchers from lots of different disciplines, deployment partners, end users, policymakers, lots of different stakeholders that might be relevant. They might not be directly on the deployment path, but they could be affected by the deployment or use of a technology. Just work with more people from outside machine learning. You're not going to obviously have interface with all of these people, but recognize that they're there, and it's important to think about some of these perspectives. There is a useful figure that you might want to look into afterwards called Arnstein's ladder of citizen participation. You can look at this and learn more about it. I've mostly focused on considerations for machine learning for climate projects. I want to also mention that even if you're someone who doesn't explicitly work on climate change should still be a central can still be a central consideration in how you do your general machine learning work. If you work on machine learning for better or worse, your work is probably impacting climate change. We already talked about the emissions impact from computation. You can also think about how machine learning may concentrate resources among already powerful entities and potentially widen the digital divide. Divide between different sets of stakeholders, having power and not having power. You can also think about ways to communicate responsibly around machine learning. Machine learning often gets a lot of attention and flash in a way that other fields don't. And the climate change community is often desperate for solutions given the short timescales we're facing. So it's important that we avoid techno-solutionism, going out and selling machine learning as the solution to everything in a climate change context and in other contexts. So it's important we're sort of honest and humble in our communication about the capabilities and limitations of technology in order to avoid diverting attention from other approaches to climate change that may be less flashy, right? We don't want to have machine learning be seen as the savior and sort of direct all the attention from better or lower hanging fruit when it comes to climate action. Sometimes machine learning is relevant, but it's not going to save us. So to sum up, when working on specifically climate-related problems, understand how your algorithm is situated within the broader pathway to impact, engage with stakeholders across the pathway. When working on ML in general, think about its climate impacts, emissions, equity and climate justice, and public perception of ML. So to finally wrap up, we've looked at what climate action means. We've looked at how ML can play a part in it. We've talked through research challenges. We've considered various examples, negative effects that ML can have on climate change as well, and considerations for research and deployment. Let's now look at ways to get involved, relevant communities, data sets, and other resources, and a roadmap for starting out. So there are many ways that a machine learning researcher can, or practitioner can get more involved in the climate space. First, consider including climate relevant applications within the set of problems that you're working on that motivate your work. As we've seen, these applications can be beneficial to society, but they can also be really interesting from a computer science perspective. Especially for students, consider becoming a bridge between machine learning and some other area. There's an urgent need for people who can speak multiple technical languages, like translating between machine learning and agriculture, or machine learning and electricity systems, and understanding needs and capabilities from both a methods and an applications perspective. These kinds of skills will make you very much in demand in hiring in the private sector, potentially in academia, certainly in the public sector. Private and public sectors are like, they really need people who can build bridges between different sectors here. If you're interested in pivoting more wholly into this area, there are a lot of job opportunities. Within mainstream computer science research, there's increasing demand for interdisciplinary work and expertise. Focused institutes focused on these things increasingly. There are a lot of climate tech startups, and the space is rapidly growing. Major tech companies increasingly include teams working on climate projects, and the public sector in research-focused organizations, funding agencies, and data and standards bodies. But there's just so many opportunities that one doesn't necessarily think of as an ML researcher. For example, almost every energy company is starting to think about AI. They need to hire AI people. And so if you're a person who can speak energy language and AI, that's a place that you could be. Agriculture companies, satellite monitoring agencies, in the public sector and in private startups. These are all areas where people are starting to think about machine learning, and being able to build these bridges makes you extremely, extremely hireable. There are also many ways to align existing projects with climate goals, even if you're not explicitly working on climate change. For example, by considering the ways that a deployed system is influencing societal behavior, and through considering the computational cost. Every application of machine learning affects the climate, often in multiple different ways. And finally, I want to highlight that there can also be opportunities for us to advance climate action that aren't through our work in machine learning. we are people in society, and obviously there are ways that our actions, voices can be meaningful in shaping the choices made in public policy potentially, and in many cases by our employers. If you're interested in this space, there are many more resources available. So I am a co-founder and chair of Climate Change AI, which is a global nonprofit that catalyzes impactful work at the intersection of climate change and machine learning. We have a global community of many thousands of people across many different fields and sectors, and there are ways to engage. Check out our digital resources. So that includes reports aimed at researchers, practitioners, policymakers, other stakeholders. We have events. Our next event is at, no, we actually have a symposium at AAAI, the AAAI Symposium Series, but the next big event is at NeurIPS 2023. There is a submission portal available right now for our next workshop. You can also look at past submissions. We have about 600 submissions here. We have a summer school every year, including both virtual and in-person summer schools. We have research funding. We have already given away about $3 or $4 million in research funding for impactful projects that in particular are focused on data set creation in addition to other kinds of research. Check out our website for more details. We have a newsletter, which is, if you sign up for one thing or look at one thing, I would recommend the newsletter because that gives a monthly update on everything that's happening in the area of climate change and machine learning. Events, job opportunities, new papers and data sets that have come out. It's a really valuable sort of hub for lots of information. And we also run events like webinars and happy hours. We have a digital community as well, I should have mentioned, where you can just ask questions of all of the tens of thousands of people who work in this space. So there's some other relevant resources. Outside of Climate Change AI, there are many communities and events for learning about and working in this space, including communities oriented around particular domains and sectors like energy, land use, climate and earth science, or biodiversity. I highly encourage you to check out these communities if you're interested in these various different areas. These are sort of area specific. For researchers who are interested in publishing work at the intersection of ML and climate change, there are many options. There are a growing number of papers at venues like ICML and NeurIPS and CVPR that are motivated by climate relevant problems. And these conferences now often include climate as a particular subject area. There is also a special track of the Journal of Machine Learning Research, JMLR, which is focused on climate change. A very high profile publication venue. There's environmental data science, ACM Compass, and many other things. The Climate Change AI newsletter includes a lot of updates on publication venues. And then finally, I want to touch on data sets and challenges available to get started. Here's another slide that you can take a photo of. Again, I'll share the slides afterwards. Lots of different ways to get started in this space. If you're interested in any of these areas, I recommend checking these data sets. More info on our wiki. So to finish, finally, here is a rough roadmap of the steps involved in getting started in the space of ML for climate. Start out by identifying specific key areas that you might want to work in. Maybe you're particularly interested in biodiversity monitoring, or you already have people you know working in the power sector. Maybe you have expertise with a particular machine learning tool that you want to tailor to climate relevant applications. Next, you can check out data sets or challenges to get hands-on practice. Explore and learn more about these relevant problems, remembering also to include the non-ML strategies that people are using. Often these classic approaches are very effective, and machine learning can build on them and incorporate insights from those. Find collaborators with complementary expertise in the relevant domains, work with them to identify and scope problems and data sources. There may not be established machine learning data sets, but often the most impactful work is on problems that are well known to the domain experts, but haven't yet been set up as machine learning challenges. So this is an opportunity to really have an impact. When you design your algorithms, remember to incorporate domain knowledge including deployment considerations like robustness or interpretability that need to be built in. Talk with the relevant stakeholders to better understand these factors and work with them to make sure that your work actually gets deployed impactfully. That is one outline for how you might start out in this space from square one, but there are obviously lots of different paths, and hopefully this tutorial is giving you some pointers on how to explore this space further. Thank you so much for listening to all of this long tutorial, and we have a few minutes for questions now. Thank you so much.
Thank you so much. Yeah, let's give a round of applause, I think. Yeah. Great lecture. Yeah. Great lectures, and then also like great wrap up. That I think like the knowledge that we get here can be translated to other fields too. So I think we have some questions. Yeah.
Okay. Hello. So as someone coming from like energy and chemical industry, I think applying the physical constraints into the model is really important. Recently, I have been hearing a number of data scientists working in this industry having problems convincing the stakeholders to actually trust the model. So I just wondered, because you have been presenting about incorporating that, I wonder like how mature is the field as of now, the physics-based ML, and also the constraints. Is there still any limitation that we still face when we want to apply it to the industry from your view? Yeah.
Yeah, so it really depends upon the particular application, how mature the field is. So for example, in power systems, forecasting of both demand and also supply of electricity is very robustly developed and even deployed in various power grids. That is not the case for grid control. So that is an area that's still being worked on. And one of the challenges there is, as you say, robustness and guarantees. Another challenge is just there aren't really metrics set up or processes for evaluating some of these algorithms, even if the algorithms are there. And so in that kind of context, I highlight an example of, like, I think I mentioned it here. Yeah, like L2RPN and challenges like that are really moving forward the needle on how deployment ready various algorithms are, because we're seeing this is a collaboration between various power systems operators that are looking at reinforcement learning approaches and testing them on real simulation data from their grids. So we're increasingly seeing stakeholders, even in cases where the applications aren't being deployed, testing the algorithms for deployment. And so that's sort of the next frontier. It's working with stakeholders to make sure that the algorithms are really being tested in mission critical settings so that we can trust them enough to actually deploy them.
Thank you for sharing.
Yes, thank you for a very nice overview presentation. This would galvanize the research community to kind of considering this more deeply. My question is related to how to measure the the contribution of our action in this field. So is it may I ask how important if we have to measure if there is a concrete measure in measuring the contribution in this one? Yeah,
it's a question.
Yeah, and to give some some more context into my question is that recently there is a trend on assigning carbon credit into anything that contribute to the action that push forward the effort of sustainability, if not climate change in general. So my question is two-pronged. First is it possible that we can, if there exists action of our work in terms of negative carbon credit,
yep.
And second is that it is necessary that all the investment should be pushed into this action that have a negative carbon credit in our field, whether it's help or hurt.
This is a really, really good point. So one of the reasons why carbon credits or carbon pricing systems more broadly are really useful is they incentivize all kinds of actions. Like maybe the technologies for accurate emissions monitoring or other related things can be developed are going to be catalyzed by carbon pricing systems that cause people to want to monitor emissions, and that causes people to pay for technologies that can monitor emissions, for example. So absolutely, carbon pricing is really important in leading to all kinds of technological innovation and other progress in climate action. In terms of our personal actions, we may be interested in how impactful we are being, and that may be hard to assess. It may be hard to assess for two reasons. One is it's very difficult to understand what one's personal impacts are. Suppose that I create an algorithm that's used by some number of people. I don't know who those people are, how many necessarily. Maybe I see the number of GitHub pulls or the number of stakeholders that I'm personally working with. But it's difficult to quantify, and it's difficult to quantify their impacts. Maybe they don't have a sense. What fraction of the impacts can I attribute to my work rather than their work, right? Like suppose I'm collaborating with some people and the machine learning makes it easier for them to do their job and reduce emissions, but they would have had some emissions reduction anyway. How much is due to me versus them? It's really complicated. From a carbon pricing perspective, some of these things need to be worked out in order to provide the appropriate financial incentives. Those systems have not yet been worked out. From the perspective of you feeling good about your work, don't fully worry about it. I would not worry much about whether you've reduced 100 tons of CO2 or 1,000 tons. Maybe you should be thinking in terms of orders of magnitude a bit, but think about whether you feel like you're having plausibly a meaningful impact. Because ultimately, we're not going to be able to quantify the impacts of our actions exactly. And oftentimes, the things we can quantify are the less important ones. It's very easy to tell certain kinds of small impacts and measure them, but sometimes the bigger ones are very hard to measure, and that doesn't mean that they aren't important. So sometimes it's important to be satisfied with sort of understanding that one is contributing to something that's bigger and harder to measure, and finding a middle ground between realizing that something is important, but not being able to capture exactly quantitatively how important is enough.
Got it. Thank you very much.
So my question is from the perspective of the newcomers who might be interested to get into this area. So it seems that a lot of your research work involves around science or concept of science that most ML people are not already familiar with, like crystallizations or electrolytes. My question is that when you do research on something that is interdisciplinary, do you spend a lot of time learning this domain-specific knowledge and past methods in this area? And how much understanding or how deep of the understanding do you need to be successful? Or what techniques do you use to help in achieving this understanding?
Yeah, it's a great question. So I think that generally speaking, if you're going to be successful in this area, you're probably going to both work with people who are really expert in the area. And whether you're in a research space or the private sector or the public sector, you're going to be working with people who have complementary expertise, but you're also going to gain some understanding yourself. So it's not like you need a PhD in chemistry to be working in ML for chemistry. You probably need some knowledge of chemistry, and you're probably going to get a lot of knowledge by working with the actual chemists. So it's sort of middle ground. Work with actual chemists who have really in-depth experience, but you're going to get some experience yourself. And probably over the course of a while, you're going to get really good at a basic level of chemistry, but a basic level. And you don't need the really in-depth stuff. You're also not going to be able to do this across lots of different areas. Like, I do not have in-depth knowledge of most of the application domains. My students do. Like, I have a student who's working specifically on machine learning in agriculture. He's worked with lots of different agricultural entities over the course of years, and he's built up a lot of knowledge. I have another student who works on machine learning and snow and really understands snow science. Not as much as an actual snow scientist, but knows a lot more than a typical computer scientist. I know a lot more about biodiversity than a typical computer scientist, and I am able to work with that community, but I'm not an ecologist. So it's somewhere in between like that.
All right, I think we have like one more question, and then we can wrap. Like, anyone have?
Yep.
Hi, thank you for your presentation. I'm interested in interdisciplinary research, but I'm also interested in a career in academia. I wonder what your thoughts are in terms of the conflicting objectives, because if I, for instance, work on, say, ML in climate change, but like in the hiring process, people consider me as like, are you an expert in machine learning? Are you an expert in climate change? Or because in many environments that some universities operate, there might not be much room for like cross-discipline work. Thank you.
It's a really great question, and it's a challenge. In the Climate Change AI newsletter, you can see the various hiring calls that are accelerating for academic positions in this area. The number has just continued to go up a lot. And this is positions specifically in this area. So you can see them at all levels, from PhD positions up through professorships. Now, those are specifically focused on this area. It is more challenging to get considered for positions which aren't specifically focused on this area. Like, if you are working on machine learning applied to something, sometimes that means that you're not considered to be sort of an innovator in machine learning, like in pure machine learning. That can be a challenge, and it's something that we're working on addressing at a cultural level in the field. And we're making progress because we're seeing in the pure machine learning venues like NeurIPS and ICML and JMLR, a lot more people working on climate change. So the culture is changing. There are specific calls for people to have this kind of expertise, but it needs to change more. I'm happy to talk with you. Feel free to contact any of you. Feel free to contact me privately offline afterwards if you want to discuss some of these challenges more and how to address them. I'm happy to discuss further. You can find my email online pretty easily. And so these are all really good questions, like really impressive questions. Thank you so much for listening and for joining today.
All right. Yeah. Again, thank you so much, David. Yeah, I'm here. So thank you so much again for giving such a great lecture. So if anyone interested into like more AI and climate change, I think you can follow like all the publication venues, like the tutorials and like ICML tutorials, and also like Twitter, right? Like that would be like a great place to start if you are interested in. But again, thank you so much, David. Please give a round of applause again for David. Yeah, so great lectures, and hope to see you maybe in the future, online or offline somewhere.
I hope so.
All right, so yeah, I think it's time for lunch. So thank you guys for sticking around for this morning lecture. Yep.